Okay, so welcome everybody. Hello, and welcome to our whole training series. Today we have yet another workshop dedicated to learning how to use our whole system. So today I'm very happy to again Dr. Asad Khan, who is going to give us a tutorial on how to get started with TensorFlow. I also would like to congratulate Asad with his graduation from the University of Illinois, and he's starting his new job starting from next week. So we are incredibly happy to have him for this last time to present this workshop. So Asad, let's take it from there.
Yeah, thanks a lot, Vlad. Thanks for the introduction. So just like last time, I'll start with some instructions to get started on HAL first. In case you have never used HAL before, you have to follow step 0, which is you have to fire up a terminal on your computer and then SSH into HAL login node. So just replace the username with your username and then run this command on the terminal. It will ask for your password and possibly two-factor authorization. And after that, you'll be in. So if you have never used HAL, this is essential. If you have used HAL, you can for now skip to step 1. So for step 1, then you have to go to HAL ondemand.ncsa.illinois.edu. And again, you have to log in with your username and password. Once you have logged in, it will look something like this, the screen. And you have to click on the interactive apps and select Jupyter Notebook. So once you select that, it will present you a form which looks like this. And then you just have to pick specific options. So for today, we have reserved a certain number of GPUs. So you can pick the GPU partition. For number of hours, you can select 2. The name of the reservation is UIUC_35. And then you can pick 4 CPUs and 1 GPU, which is like the minimum numbers for both. And then you can click launch. Once you click launch, I already have it running, but once you click launch, then first it will give you a message that the job is pending, and then finally it will be running. And then you can click connect, and it will take you to your home directory on the HAL cluster. So that's step 2. I've also written it here. We are pasting the URL for this document in the chat as well, so you can follow it at your own pace. But once step 2 is done, then the last step is to clone the repository which has the code for today's tutorial. So we are in this second tutorial by me, which is called Intro to TensorFlow. And so for this, you just have to go to your home directory on the terminal and run this command, git clone, and you have to specify this URL, which, by the way, if you click the URL, it should take you to a repository on GitHub as well. And so for this last step, once again, you have to SSH into the terminal. That's one way. Or you can, once this job is running, you can also click new and then click terminal here. So you have both options. And then in your home directory, you just have to do git clone and the URL. So you just copy paste this. So once again, I'll give everyone a couple of minutes to go through these steps so that you have a Jupyter Notebook running and you have successfully cloned the repository. Okay, I'm going to presume it's a significant number of people have gone through these steps. If you're still, if you're having any problems, definitely post it in the chat. Also, if you need a little bit more time, please post it in the chat so I can decide whether to proceed or not. Okay, I see one question. If you're having trouble with cloning the repository, once again, you can go to step 0. So you have to fire up a terminal on your computer and SSH into Hall login node, and then you can just copy paste this command. Or if you can also go to Jupyter Notebook if you have that running, and you can just click new, and at the very bottom it should be terminal. It should say terminal. So if you click that, then it should fire up a terminal, and you will by default be at your home directory. And so then you can just do copy paste this command here. And if you run this, it should clone the terminal to your home directory. I can also paste this in the chat. Okay, so then I'm just going to go ahead and get started with the actual tutorial. So for today's tutorial, we have 2 notebooks. Once again, I apologize, they're listed in the opposite order. We are first going to go through tensors, variables, and derivatives, and then through layers, models, and training. So we're going to go through the simpler ideas, the more fundamental ideas, and then build up. So if you have cloned the repository to your home directory, you just need to go into that repository, click that, and then you should see these 2 notebooks within it. So let's just click the tensors, variables, and derivatives notebook. So one last thing, by default, you might not have the correct Conda environment. If you're not seeing Conda and OpenCV-version 1.3.1, if you're not seeing this on the top right, then you have to click kernel, change kernel, and then pick OpenCV version 1.3.1. That's only if by default you're not seeing the right environment. So just please make sure that it's running the right environment. If it is, then you can import the libraries, you can run the first cell, and it should run successfully. It should take a little while. It might take a little while, but it should run. Okay, so for today's tutorial, if you came to my last tutorial, we just went through some fundamental ideas about deep learning. We first discussed them theoretically a little bit, and then we quickly went and started building neural networks and training them on toy data sets. So that if you came to that tutorial, hopefully that gives you some higher level picture of what deep learning is. In this tutorial, my hope is to go into more fundamentals of a deep learning API. So there are different APIs specifically tailored for deep learning. One is TensorFlow, there's PyTorch, and then there's a few upcoming ones. But by far, I think TensorFlow and PyTorch are the most popular. And last time we worked with TensorFlow, so I'm going to stick with TensorFlow for today's tutorial as well. But once again, just a few words between the similarities and differences between TensorFlow and PyTorch. They used to be significantly different, but now they're sort of converging. So if you learn TensorFlow, it shouldn't be a problem switching to PyTorch and vice versa. So the hope today is just to go into the API and learn more about the fundamentals of the API. So you can do maybe perhaps more advanced stuff with deep learning. So you can move from those toy problems that we discussed, and you can perhaps move into your own research problems and start building more complex workflows. So I thought a good starting point once again would be linear regression. This is how we started last time. Because this brings about, once again, the fundamental ideas involved in an API as well. So remember, for linear regression, we are fitting to a straight line. We have some input data, x, and some output data, y. So this will be our input, this will be our labels or outputs. And then we're trying to learn the parameters M and B so that our predictions are as close as possible to the outputs, okay? So we input our x's and we adjust M and B, our learnable parameters, so that our predicted values are close to y, okay? So this was, these were the steps involved last time. First, we collect our predictions. So we first start with some random guesses for M and B. And we input all our x values. So that gives us our predicted values, which we denote by y tilde, right? So for each input xi, we have corresponding prediction, yi, y tilde I. Then given those predictions, we check how close those predictions are to the ground truth values. So the ground truth values are y_k here. And then these are predicted values. So we just difference them and square them. And this is the mean squared error. And we normalize by the number of examples we have. So this mean square error is also referred to as the loss. And depending on the problem, we'll change the definition of our loss will change. But for fitting to a straight line, we used mean squared error last time. Then we used gradient descent. And the idea there was, given this loss, we compute the derivatives with respect to our learnable parameters, which are M and B here, right? So mathematically, we know how to compute those exactly. So we found those out. And then we just input these values into the formula that gives us the derivative at that point with our guesses M and B. And then we just update them, M and B. So remember, the gradient points in the direction of steepest descent. So if we take a small step in the opposite direction, then this loss should start decreasing. And that's what we're doing. So we're taking a small step, which is tuned by this alpha parameter, which is called the learning rate. And we take a small step in the opposite direction. And this is how we update our parameters M and B. And so we keep repeating this until our loss converges to a minimum. Okay. So this was the idea last time. And this immediately shows some fundamental ideas when we go to an API. So in API, the fundamental objects are tensors and variables. Okay, so tensors are fixed data types. So these could be numbers, vectors, matrices, and so on. And in our case, the data that's given to us is fixed. So that's tensor. And then variable, as the name suggests, is what we're trying to learn. So M and B are variables here. So that's first thing. And then the second thing is doing this whole computation. So what a deep learning API hopes to achieve is so that we don't have to mathematically, write out all these formulas by hand and then write them out in code as well. What we expect from an API is that it can keep track of the forward computation and then compute the derivatives automatically based on that forward computation. And how a deep learning API achieves that is by building a computational graph. So computational graph can be represented like so. We just have nodes and operations. So we have this node which takes the input, this node which has our learnable parameter W. And then at this node, we just multiply them together. Then we take the output, go to the next node where we add it to the next learnable parameter, the bias vector B. That gives us our output. Then we take it to some kind of function, which here it's mislabeled to CE, but in our case, it's MSE, right? Mean squared error. So just ignore that. But here, for example, we compute the mean squared error based on our prediction and the ground truth value. And that gives us the loss, okay? So then if we keep track of all of these operations and keep a cache of values at each of these nodes, then it becomes very easy to automatically differentiate. We can go back and implement the backpropagation algorithm, okay? So you can learn more about computational graphs, but the essential ideas involved in a deep learning API are 1, tensors, 2, variables, third, building a computational graph, and then being able to automatically differentiate and do backpropagation based on that computational graph. So those are the 4 fundamental things involved here. So we'll just go through each of them quickly. So first, tensors. What are tensors? So tensors are very similar to Numpy arrays. If you have worked with Numpy or NumPy, then the lists or vectors that you can pass to np.array. Similarly, here we can create tensors, and their behavior and description and definition is very similar to Numpy arrays. So how do we define a tensor? So there are 3 fundamental properties. First is shape, which is the length of each of the axes, right? So for example, if we have a matrix, then we have 2 axes. And then, so by shape, we just mean the length of each of those axes, right? So how many rows we have and how many columns we have. So matrix can be 3 by 4, 5 by 10, whatever have you, and that would be the shape. Rank basically says how many axes there are to begin with. So a matrix has 2 axes, so it's a rank 2 tensor. But a vector, for example, has only 1 axis, it's a rank 1, and a scalar has a rank 0. And then size is just the total number of elements inside a tensor. So let's say if it was a 3-dimensional vector, then there are 3 elements in it, and the size would be 3. If we have a 3 by 3 matrix, then we would have 9 elements, and the size would be 9. So those 3 things define a tensor. In addition, we'll also define what kind of data type. So what is each element inside a tensor? So let's actually begin by instantiating a tensor. So instantiating a tensor is very simple. You can just call TF. Remember, TF corresponds to TensorFlow. So up here, we imported TensorFlow as TF. So from now on, we'll just refer to as TF. So we can call TF.constant. Then we just passed a list or a list of a list, depending on the rank, right? So here, we just pass this, and then we can just print this tensor as well as check its data type and its shape. So if we do this, okay. So by default, it just assumed that the data type is int 32, and then the shape is 3 by 3. This is a matrix. Yeah. So that actually suggests we should be able to change the data type as well. So you can do that easily. So once again, we are just instantiating the same matrix, but this time we can specify the data type. So instead of, let's say, int 32, maybe you want it to be a float, and then you can pick between float 32 or float 64. So you can explicitly describe the data type as well. So that just tells you what each element is. Then similar to Numpy, you can also create tensors, constant tensors. So if you're familiar with Numpy, then you've probably seen something like np.zeros and np.ones. Same idea here. You can call tf.zeros or tf.ones, and it will give you TensorFlow tensors. And you just have to describe the shape of the tensor that you want. So maybe we create a 1 by 6 tensor of zeros, 2 by 3 tensor of ones. And if you want some other constant, then you can just call tf.constant, specify the constant that you want, and then the shape. So that's how you would instantiate constants. But you can also sample from many different distributions, probability distributions. So this is again similar to Numpy. You can go to tf tensorflow.random and check all the distributions that you have available. But for example, you can pick the normal distribution. And once again, the idea is you specify the shape. For normal distribution, you also have to give the mean and the standard deviation. And then similarly, you can pick, for example, the uniform distribution. Here, this will be an interval. So you just have to define, describe the minimum and the maximum. Or you can go to Poisson distribution, and then you just have to define the lambda. Okay, and you can look into how many other distributions that are available to you. So here, basically, it will randomly sample from the the distribution that you describe, and then it will fill the tensor with those samples. So let's just run this and see what happens. So this is our zeros tensor, ones tensor, eights tensor, and then here's our tensors that were sampled from normal distribution, uniform, and Poisson. Okay. Lastly, we already talked about ranks, but once again, rank 0 is a scalar. So you can just call tf.constant, just give it a number, and that's a scalar. So that would be a rank 0 tensor. You can give it a list, which is a vector. So that's a rank 1. You can give it a matrix, but you can also go to higher ranks, right? So you can go to rank 3, rank 4, and whatever. And then given a tensor, you can quickly check all of these properties about it as well. So you can check the rank of a tensor by just calling tf.rank and passing your tensor. Or similarly, you can just call your tensor dot rank. Okay. So for shape, I'm doing the other style. So for this tensor, I can call dot shape, and it will give me the shape. Similarly, you can also find the size. So if you just run this, then it will give you the rank. So this is a rank 2 tensor, this is rank 3 tensor. The shape of rank 2 tensor is 3 by 2. So the shape of rank 3 tensor happens to be 3 by 2 by 5. Of course, here we just specified it, but given any tensor, you can call these methods on them. And then this gives you the size, which is the total number of elements in it. Okay, so what can we do with the tensor? Again, similar to Numpy arrays, most math operations also apply to tensors. So let's say I have two tensors A and B, then I can add them together element-wise, subtract them. I can do an element-wise multiplication. And if the shapes are legal, then I can also do matrix multiplication, right? So you can just do that by calling tf.add, tf.subtract, multiply, and so on. And then once again, you can look at the documentation and look at all the math operations you have. But for these basic operations, you can also do operator overloading is available, just as in Numpy. So you can actually use the plus minus sign for element-wise multiplication. You use the star, and then for matrix multiplication, you use the add symbol. That should also do the same thing. Few other things, you can take the absolute value, you can also raise one tensor to the power of another, and so on. I think perhaps one thing I forgot to mention, but it was listed at the very top. The important property of tensors is that they are immutable. So whenever we are doing these operations, we're not changing the tensor, we are actually creating a new tensor, right? So when I call a plus b, it creates a new tensor, c for me, which has this value. So immutable basically means you cannot change a tensor once you instantiate it. Okay, so that's very important to remember about tensors. And if you remember in my example above, our data was represented as a tensor, so it makes sense. Given a data, it should be immutable. We don't want to change the data itself. Based on the data, we're trying to learn a few parameters for our model. Okay. Then similar to Numpy arrays, once again, you can also indexing, slicing, and reshaping also works very similarly, right? So given a tensor, we can pick the elements from index 1 to 3 here. So you can do slicing using colons, but you can also just call tf.slice. Then you just have to give the starting index and then the size. So starting from this index, how many elements do you want? Those are available. Then you can also reshape a tensor similar to Numpy arrays. So here, for example, I start with a rank 1 tensor, and then I can change it to rank 2 tensors or rank 3 tensors as long as the sizes are legal, right? So the number of elements have to stay constant. So I have 16 elements, and I can change it to, let's say, shape 8 by 2, that's still 16 elements, or 4 by 4, that's still 16 elements, or 2 by 2 by 2 by 2, so that's a rank 4 tensor. So again, these are immutable. So I'm based on this, I'm just creating new tensors with different shapes. So I can call tf.constant, pass my x tensor, and then give it a shape, a new one, right? So here it's 8 by 2 or 4 by 4, 2 by 2 by 2. And then let's print those. And so you can see the elements are still the same. It makes a copy, but the shapes are different now. Another convenient thing that you can do is you can add a redundant dimension. So let's say our tensor C here has shape 2 by 2 by 2 by 2. I can add a redundant dimension at any index. And that's what this tf.expand dims is doing. So I can add another dimension at 0th index, 1st index, 3rd index, and so on. So if you run this, you would see this C tensor changes from 2 by 2 by 2 by 2 to here. We have another dimension, 1 here at the 0th index or the 1st index or the 3rd index. And then we can also go backwards. If you have this redundant dimension, then you can also get rid of it by calling tf.squeeze. And so you might be wondering about this dimension, but if you remember batch sizes, sometimes you perhaps need to add another dimension at 0th index to accommodate for batches. And after training, perhaps once you have made the prediction, then you might want to get rid of this dimension. So that's the only reason, well, one of the reasons I'm mentioning this method here. And then the last thing is, a lot of times the raw data that you would have, you would read from your disk, will be Numpy arrays, right? So is there a convenient function to convert between Numpy arrays and TensorFlow tensors and vice versa, right? And the answer is yes, it's very simple. So let's say if you have a Numpy array, here I'm just creating a Numpy array, you can convert it to tensor very easily, similar to like last time. Instead of passing an array, we passed a list, but you can also pass an Numpy array. You can specify the data type for it, and that will give you a TensorFlow tensor. And if you have a tensor, then you can convert it back to Numpy array by just calling .numpy on it. So very simple, going back and forth between these two. So here, for example, once I read the data, before passing it to my model, I might want to convert it to a tensor. And then after I make a prediction, let's say I might want to convert it back to Numpy array. So then you'll have to follow these two steps. Okay, so that's all I'm going to say about tensors. Are there any questions? In the chat, I see one question: what's the difference between TensorFlow's tensor and PyTorch's tensor? Other than like some methods that might be available in PyTorch that are not available in TensorFlow or vice versa, conceptually, there is no difference, I think. I think PyTorch might use the same name tensor for tensors and variables. I have to double check that. But there might be naming convention issue there as well. But at the end of the day, you would have two types of tensors, one that are immutable, and then those that are mutable. And so in TensorFlow, we call the first type just tensors and the second type variables. So let's move on to variables then, okay? And I think this might be very obvious to you, but why do we even need variables, right? So remember, when we are training, we are updating those M and P parameters. And if we only had access to immutable tensors, then that wouldn't work because we do want one reference whose values are changing. So then variables are essentially that. These are tensors where the values can change. So how do we instantiate variables? Again, very similar to tensors. We can just call tf.variable. We can give the initial value. So in this case, I'm passing a tensor to instantiate this variable, but you can also pass a list, I think a Numpy array, or just a number as well. All right. See, for a variable, you do have to give some initial value, which will specify its shape, data type, and rank and so on, right? So this is how you instantiate a variable. But once you have instantiated it, you can assign new values to it, right? So variables are mutable. So I'm just calling the same variable and then calling .assign on it and passing a new tensor, which is a zeros tensor 2 by 2. So this was a 2 by 2. This is how I instantiated it. And so now I can give any other 2 by 2 tensor to it or a matrix to it and change the values. So after I call this, then it just becomes a zeros. So it was initially 1, 2, 3, 4, and now it's zeros. You can also do indexing and slicing and then just assign a subset of those to new values. So here, for example, picking all the rows, but for only the first column and assigning ones to it, right? So then this zeros remain zeros and these become 1 here. And then lastly, the most important one, I suppose, is adding and subtracting new values from your variable, right? So I can add a new tensor to my variable or subtract, and you can do that by calling assign add or assign sub. Okay. So here just I'm adding ones and then I'm subtracting ones. So we go from this to this one and then back to the original one. Okay. We can also apply other math operations to a variable, but the returned object will be a tensor. It won't be a variable anymore. So for example, here I'm instantiating 2 variables. And then you can add them together or you can do matrix multiplication, but the returned object will be a tensor. Okay, so just keep that in mind. And then last thing is once you instantiate a variable, you cannot change its shape. So tensor, remember, of course, tensors are immutable. So we were never actually changing its shape, but we were creating new tensors. But here you cannot do something similar because a variable, once you instantiate it, it will be of a fixed type and shape. So for example, if you try to do something like this, you try to assign to this variable a another tensor of a different shape. So this is 3 by 2, and this is actually 2 by 2, then it will throw an error. Okay. And again, this is because, for example, going back up to a linear regression or learnable parameters, once we decide what your shape is, you shouldn't really be changing that in the middle of training, right? That gets fixed initially at the instantiating stage. And then lastly, you can also name your variables, and this is very handy to keep track of your learnable variables, especially as we go to deep neural networks where you will have millions of variables. A lot of times it's a lot easier to go back to some variable and look at its values if you had already given them names. Okay, so how do you give a name? So once again, you can instantiate a variable and then you can specify its data type, and then you can just say name equals, and you can pass a string with the name. So here, if we print them, then you can print your name by calling x.name, y.name, and it will return string underscore var and float underscore var. So that's all about variables. Any questions up until here? Okay, if not, then next topic is automatic differentiation. So if you go up, remember we said there are 4 fundamental ideas: tensors, variables, building a computation graph, and automatic differentiation. So let's just talk about these last 2 now. So the way you do automatic differentiation is first you have to tell TensorFlow whether to build the computational graph or not. By default, it will not build the computational graph because that's sort of expensive. So you don't want to do it by default for everything. But when you do require the derivatives, then you have to explicitly tell TensorFlow to build a graph. And so the way you do that is you call this tf.gradient_tape, okay? And then any computation that you do within the context of tf.gradient_tape will be kept, TensorFlow will keep a record of it in a computational graph. And so then you can come out of the tape and take derivatives. So let me just give you an example. Might be easier that way. So first, let's say I have some variable x, and I give it some initial value. Then I'm going to do something with x, but I want to keep track of it in a computational graph. So I proceed like this. First, I call tf.gradient_tape. So I start with tf.gradient_tape, and I give it some name as tape, right? I just call it tape. So within the context of this gradient tape, I square x, the variable x, right? So I'm just calling tf.square. I mean, in fact, you could have also done x squared, so you don't really need to do that. So you have both options. So you square it, and then you come out of it, and now for example, I'm interested in dy dx, right? Which happens to be 2x. So then I can compute that by just calling tape.gradient of y with respect to x, okay? And remember, any computation I do will give me a tensor, and then I can convert that tensor to a Numpy array by calling .numpy. So let's just do that. And as expected, I get 10, right? Because x was 5, so 2 times x is 10. Now, one thing to remember here is that gradient tape will only keep track of variables, specifically trainable variables. So variables, we'll see you can change the property whether they're trainable or not. But gradient tape only keeps track of trainable variables. So by default, it will not keep track of tensors. So let's say if x was a constant tensor, then if you did this computation with gradient tape, it will throw an error if you try to find the gradient. But there is a way around it. You can specifically ask the tape to watch x. Then it will keep track of the gradients as well. So in special circumstances where you're doing something to a tensor and you want the derivative with respect to those tensors, then you can just specifically ask the tape to watch those tensors. By default, the idea is that you would not need to do that. Now, you're only interested in updating variables. Okay, so here I'm doing the same thing, instantiating a tensor, and then just calling tape.watch, and then doing, again, squaring it, and then once again, the same thing, and I should get the same number. So here I'm just taking gradient of the output with respect to one input, but you can also do this with respect to multiple inputs, right? So again, if we go back to our example of linear regression or fitting to a straight line, it's y equals mx plus b or x times w plus b. And then just for fun, let's also square y, right? So we're doing 2 steps. So w and b are our learnable variables. Instantiate them with some random values, 1 and 2, give them a name as well. Then my input is just the number 5 here. So once again, I start a gradient tape, I do this computation, I square it, and now I can take the derivative of z with respect to w as well as with respect to b. Both of these are variables. So we can do that easily by just calling tape.gradient of z, and then you just pass a list of variables that you want the gradient with respect to. So here with w and b, and this will return dz/dw and dz/db. Yeah, and now, so hopefully you get the idea. So if we have a deep neural network with millions of parameters, then we can just pass all those millions of parameters in a list. And just in one line, it will give us the gradient of the output with respect to all of those parameters. Also, you can take the gradient, of course, with respect to intermediate results. So here we did it in 2 steps. You can find the derivative of z with respect to w and b, but you can also find the derivative of z with respect to y, right? So you can also call div.gradient, give me the gradient of z with respect to y. So that also works. You probably would not use this very often, but just for completeness, you can also take higher order derivatives. So for example, you can take a second order derivative by just instantiating 2 gradient tapes instead of 1, right? So to set an example for that, let's just consider a freely falling object in Earth's gravity. Then we know that from basic physics that the distance covered is given by this formula, distance equals half at squared, assuming that we started with 0 initial speed, right? We just release something and it drops. And then, of course, the speed or the velocity is the derivative of distance or displacement with respect to time, and then acceleration is the derivative of velocity with respect to time, right? So let's do that here. Let's take the second order derivative. So first, I start a variable called time, represented as t. Acceleration is of course a constant given by Earth's gravity. It's 9.8 meters per second square. So that's a constant tensor. And then I'm starting another tensor called clock, which basically I can give different values at the clock to my time variable, right? So I might be interested in what is the distance covered and speed at 1 second, or I could be interested at 10 seconds, right? So I can just change it here and just assign it to my time variable. So that's what I'm doing here. Let's say I'm just interested in what happens after 1 second of falling. Then I just instantiate 2 gradient tapes. So I start div.gradient tape as outer tape and then also inner tape. So within the inner tape, I just compute the distance, which is half at squared, right? Now, since this was done within the context of inner tape, I can come out of it and compute the speed, right? Which is, I can take the derivative of distance with respect to time. It will give me the speed. This is outside the context of the inner tape. But since I computed speed within the context of the outer tape now I can come out of the outer tape and compute another derivative of speed with respect to time, and that should give me acceleration. So that's the idea, how you can take higher order derivatives by opening multiple gradient tapes. So then after 1 second, we can print what is the speed and what is the acceleration. And since we started from rest, after 1 second, speed is 9.8 meters per second, and acceleration, of course, should always be constant at 9.8 meters per second squared. Okay, so that's all about computational graphs and gradient tapes. I'll take any questions if you have right now. Okay, if no questions, then let's go back to the linear regression example that I did at the very start of my last tutorial last week, and just write it out once again with the new tools that we have. So remember last time I started with this equation, y equals 2x, and then I just added some random noise to it. And then for my initial guesses for M and B, I just took some random numbers, and then this was my initial guess, and just M and B are randomly initialized, so I just multiply M with the input X and add the bias B. That gives me the predictions, and then I'm just plotting both my data, which are X and Y here, and as well as my guess line right here. Let's do that. Okay, so that's my data. This is my first guess. Last time, if you remember, these were the steps we did. We picked learning rate alpha, which attenuates how big of a step we're going to take. We decided for how many epochs we were going to train. So remember, epoch is going through all of the data for gradient descent once. And last time we went for 10,000 epochs. Then for each epoch, we basically repeat these steps, right? We collect the predictions, we compute the loss, which is a mean square error. We computed the derivatives of the loss with respect to M and B. And here I had to write it out, right? So on pen and paper, for example, I had to write out what the derivatives were and then just write those out in code here, for example. And then you could update the parameters like so. So this is what we did last time, but now with the gradient tapes and computational graphs, perhaps we can automate these steps, right? We don't need to work out what the derivatives are with respect to M and B. We would let TensorFlow figure it out on its own. So let's do this example once again. So this time, my M and B, which we are updating, are variables. So I instantiate those. I'm just calling them capital M and B to differentiate from the numerical values. Then my data is tensor. So I'm just calling tf.constant and converting those into constant tensors. Then once again, same alpha, same number of epochs. For each epoch now, first we instantiate a gradient tape because we want to keep track of these computations. So instantiate a gradient tape, I do the forward pass, collect the predictions, compute the loss, still the mean square error. But now I come out of the gradient tape and let TensorFlow figure out what the derivatives are by calling tape.gradient of loss with respect to M and B. Those are my learnable parameters. So I don't have to work out the math. It will automatically figure it out. And once I have those, then I can update my parameters. So I can do m.assign sub. So I'm subtracting my learning rate times derivative with respect to M. And for B, same thing with respect to B. And we can run this again. And just like last time, you should see that as the epochs are progressing, the loss is decreasing. For you, if you requested a GPU, this should be significantly faster, but I'm on a CPU node, so it's slightly slower. And then once this is done, then you can, again, see what does the prediction look like now. And we have a pretty good looking prediction now. So that's the end of this notebook. The 3 or 4 fundamental ideas, which are tensors, variables, computational graph, and automatic differentiation. So we covered that here, and I'll take any questions if you have about those. So I have one question. Can we move the tape outside of the training loop? Of course, you can start the gradient tape anywhere. Oh, I see what you mean. So if you mean this, and then moving all of that, right? Is that what you mean? Well, if you mean this, then I would say this is, feel free to like unmute yourself and you can also tell me. So track it once, what does that mean?
I was wondering, like, since you're only really evaluating the gradient at different point, can you just like evaluate, like just track the gradient once, like outside of the training loop, and just call the tape.gradient at different point to evaluate the value?
Oh, I see. I see. I see what you mean. I think this might be doable somehow, but I think at each point, then you would have to name your variables differently, right? So at each epoch, for example, this would be, you know, loss epoch. I would have to name it like so. So then when I come out of it, then I can do, because I give the losses here and then the variables like at each point. Something like that might be doable. I'm not exactly sure, but Yeah, if there's a clean way of writing it, let me know. I can't think of a succinct way of writing it, but of course that's possible to do that. Another thing is like this for loop. I mean, so you don't want to keep track of anything unnecessarily, right? So any step that where you don't require the gradient, you shouldn't have that under a gradient tape, right? So for example, I'm doing this for loop, it's doing these subtraction additions. Well, you might not do this if it's outside, but you get the point. If there's like unnecessary computation where you don't need the gradient, then you do not want that inside a gradient tape, because this is computationally expensive. It is building up a graph of all the computations you're doing. So that's why ideally you would only start a gradient tape and do just the bit of computation where you want the computational graph under it. Does that make sense?
I see, yeah, thank you.
Yeah, no problem. Any other questions? Okay, if not, then we can move to the next notebook, and I'll just motivate the next notebook by saying a few words here. If you notice, we are still doing a lot of things by hand, right? We are still doing the forward pass explicitly. So this happens to be just one layer. We have one linear regression line. But let's say if it was like hundreds of layers, then this forward pass, just writing it out by hand below a gradient tape can look messy. And then computing the gradient as well. Here you would have to pass like a long list of all the variables that you want the gradient with respect to. So perhaps we can build something which can abstract the forward pass and the learnable variables together into one object. And that object is called a layer. So let's go to the next notebook called Layers, Models, and Training. And now we'll see how we can start building up layers and from the layers models and then how to train them. Okay, once again, just a quick reminder, if you're seeing a different kernel here, you have to go and pick OpenCE 1.3.1. Okay, so for example, for me, even it was the wrong kernel. So just make sure this is the right kernel that on the top right, and then you should be good to go. So once again, we load some libraries, just Numpy, TensorFlow, and Matplotlib. And then, yeah, let's move to layers. So layers abstract both the learnable parameters and the forward computation together into one abstract object, okay? So once you define it, you can collect those two together into one object, and then you can reuse it again and again, right? So for example, for linear regression, I can use the same idea over and over again without having to rewrite it. This is the basic object-oriented programming idea. So you don't have to rewrite the same thing again and again. So that's a layer. And in TensorFlow, it's very simple to define those. And once again, within TensorFlow, we'll mostly be working with Keras. So TensorFlow is sort of a bigger API. It has other submodules, but Keras is the main one that we'll be working with, and it almost has everything that we need. So you can actually define layers within just TensorFlow, like tf.layers, but that's even a more fundamental level layer, but you would hardly ever need that. So you can always go to tf.keras and then just call the layer. So to define a layer, we subclass from this, okay? So we, again, if you have worked with classes in Python before, this should be straightforward to you. So I'm defining a new class, which is a subclass of this layers class available in tf.keras. So I'm just going to define a dense layer, which again, if you remember, was a fully connected layer from last time. or a linear regression line, straight line. I'm just going to call it my dance. Okay. So it has two essential things you have to do for defining a class. First, you have to initialize it. And during initialization, I have to give it the input dimension and the output dimension, right? So remember, if you were dealing in one dimensions, then x and y were both numbers. But if x was, let's say, 3-dimensional and y was 4-dimensional, then my learnable parameter m would be a matrix, right? So in order to initialize learnable matrix of the correct dimensions, then you have to know what's your input dimension and what's your output dimension. So during initialization, you have to specify those. The input dimension, I'm just calling it in features and out features here. And then you can initialize your learnable variables. So there's the matrix W, which we initialize with a normal distribution tensor, right? So I'm just calling a normal a tensor that's sampled from normal distribution. So that's how I initialize this variable, and I give it a name W. And then for the bias vector or the y-intercept, another variable, and this time I'm just initializing it as zeros, right? So I start a zeros tensor and just pass it as the initial value for my variable B. Okay, once I've initialized the variables, then I have to define call, which says what happens in a forward pass, like what is it supposed to do. And that's very simple. Given an input, I'm just multiplying that with my W matrix and just adding the y-intercept B, right? That gives me Y. And sorry, let's just get rid of this for now. And we just return Y. Okay. So now I have encapsulated both my learnable parameters and the forward pass into one object called my dense. And then the beauty of this becomes obvious once you start using them. So now how do I use this? I initialize, let's say, some layer called simple layer. It's an instance of my dense layer. So I can also give this a name. I define the number of input dimensions and the number of output dimensions. So x is a 2-dimensional vector and y is 4-dimensional vector. And once I have this layer, then forward computation is very simple. I just pass my input to this layer and it gives me the output y. Okay. So x, for example, here I'm initializing as again a normal tensor, random normal tensor, and then I just pass it into y. Sorry, into simple layer, and it gives me the output y. Okay. Just call that. All right. You might be wondering, I said the input dimension is 2 and output dimension is 4, but here you're seeing like 4 by 2 and then 4 by 4. If that's confusing to you, then I'll remind you about batches once again. So what this means is that I have 4 input data points, each are of dimension 2, right? I have 4 2-dimensional vectors. So first, the 0th index is always a batch. It's the number of instances I have. So input dimension is still 2, as expected. And then when I pass it through my simple layer, then I get a 4-dimensional output. But since I had 4 inputs, then I should also have 4 outputs. So 1, 2, 3, 4 outputs, and each of those should be 4-dimensional vectors. So hopefully that's clear. Okay, so now, I don't, if I want to like do this again and again, I can just start another layer. So this would be like simple layer 0, and then this would be simple layer 1. Give it different names, right? And I can do very simply something like this, right? So hopefully you can see like this is a lot cleaner than if I had to instantiate 4 different variables and then do this forward pass by hand. And it also gives me flexibility about like how many layers I want to instantiate, how many times I want to do this. I don't have to change my code a lot. Okay, so far so good, but one thing which is very convenient is that you don't necessarily have to give the input dimensions by hand, okay, until you actually pass the data. So in a lot of instances, for example, I want to create a neural network, but I don't want to right now focus about what is the dimension of my input data. I just want to create a structure, and then it should be able to adjust to whatever data I give it, right? So you can easily do that by calling this build method. So then what happens is, instead of initializing your variables within the init method, it will initialize the variables only once you pass the data to the layer, okay? So if you look at the difference between my dense layer previously and my dense layer here, it should only be that within the init method, I'm not initializing any variables. So units here just correspond to the number of output dimensions, and I'm not caring about the number of input dimensions here at all. So I just pick that, and then within build, I initialize the variables, right? So again, it's very similar, normal distribution tensor, but the shape, I just get it from this input shape argument. And so based on that, I initialize the variables. And where does this come from? Well, this comes from your input. When you call this layer, the build method will run on the inputs. It will, for the first time, it will initialize these variables. And once they're initialized, then it won't repeat the step. Okay, so let's look at this. Just calling it flexible layer. So now I'm just only caring about the output dimension. Okay, so this is how I instantiate my layer. I don't worry about the input dimensions. And then let's say I have this data, which happens to be 2 by 2, and then I just call it, and it will give me the output, which is again 4-dimensional as expected. So that just happens to be convenient. I don't know if you remember last time when we were building neural networks, we were never caring about the input dimension, right? Except for the very first layer. We specified it, and afterwards it figured out on its own. So this is how sort of how you can achieve that. Now, once you have a layer, then you can look inside it and see what are the learnable variables, how many of those you have, and what are their values at any given time. So if you just call layer.variables, it should return all the variables. So there is the W variable, it has shape 2 by 4, happens to have these values at the moment. And then there is the y-intercept or bias vector, happens to have shape 4, and it should be zeros. Okay. And then you can also pick any of the variables by their name. So I can just call flexible layer .b, and it should pick the bias vector. So remember, we gave them names to the variables, and that's why they're useful. So we can pick them by their names. Okay, so one more thing that could be useful sometimes is by default, all these variables are trainable. So when we start using these layers in our neural network, the computational graph will keep track of all of the variables and update them all. But sometimes perhaps you might want to put some constraints, which could be physics inspired or based on your problem. You want to put them and you don't want to change those constraints, right? Then you can specifically tell that certain variables are not trainable. And so then their values will not update as you train the model. And so you can do that easily by just, when you're initializing in the build method, you can call trainable and set it to true or false, depending on whether you want to them to be able to update or not. Okay, so here, for example, just for the sake of an example, the bias vector is zeros, and we just set it to be false. It's not trainable. So now when you initialize it, it should work similar to last time, but if you look inside the layer, So you can, for example, look at the weights, but you can also look at specifically trainable or non-trainable weights. So you can also call my new layer dot non-trainable weights. So let's just run this. And so first of all, weights will just return the number of weights you have, the total number, which happens to be 2, because you have the W matrix and the V vector, so 2. But out of those 2, 1 is non-trainable, right? So when you call non-trainable weights, it returns 1. And then you can also look at the values for the trainable weights and non-trainable weights. So non-trainable, as expected, is the zeros vector. Okay, so we can keep going into this, but I'm just trying to give the essentials here. So initializing the layer is important. Controlling whether some variables are trainable or not is important. And the last thing that's important is you can change the behavior of your layer depending on whether you're in the training mode or inference mode. Okay, and just to give you an example of such a layer, we'll build our own dropout layer. So if you remember dropout, it basically zeroes out a few neurons randomly during your forward pass. But you only want to apply that during training. During inference, you don't want to zero out your neurons. So this method usually helps with overtraining, and that's why you usually only use it during training. So a dropout layer would be an example of a layer whose behavior is different depending on whether you're in training stage or in inference stage. So you can achieve that very easily. Once again, in your call method, you have to give an extra argument training, and you can when you're instantiating your layer. When you're using your layer, you can like set this to be true or false, and then the behavior will change. So in the call, we use this training argument, and if training is true, then we do the dropout randomly, which happens to be a layer. So we're kind of cheating. We're already using the layer from TensorFlow, but only during training. And then if not during inference, then we just pass the inputs unchanged, right? So that's a layer whose behavior will change. So let's just see that. We instantiate our dropout, custom dropout layer. The probability we just give 0.5. So half of neurons will randomly be zeroed out during training. Then our input data is just a random normal variable again. Oh, sorry, tensor. Then let's just look at the output during training and during inference. So during training, we pass the input into our layer, and we just set training to true. And during inference, we set it to false. And oops, we have to define it first. And you would see during training, 2 of the neurons got zeroed out, but during inference, we just get the output as is. Okay, so that's all about layers, but so besides layers being sort of pretty code-wise, their true power comes in being when you can recursively compose them together, right? That's where their true power sort of lies. So what I mean by recursively composable is that you can create new layers whose variables are layers as well. So instead of being truly variables, you can just pass other layers to initialize your new layer. So for example, I'm just creating here a multiple layer perceptron block. So it happens to be a layer, but I initialize it by passing other layers into it. So I just pass 3 dense layers. So we defined my dense up above, a few sections above, and we are using those to initialize this layer, right? So the first layer takes you to 32 dimension, the second layer again takes you to 32 dimension, and the last layer takes you to 1 dimension. And then in the call method, we just use those layers to define the call. So we pass our inputs through the first tense layer, then maybe through some nonlinear activation like ReLU, then the second tense layer, another nonlinear activation, and then through the last tense layer. So now you can treat this whole thing as one layer too. And what this will do is it will recursively keep track of the trainable variables within each of those layers. So you don't have to specifically tell it, but it will keep track of those. And it will update all of the trainable variables within those layers as well. So that's where it starts becoming very powerful. So now we can just instantiate our multiple layer perceptron block, pass our input through it, and let's look at a few properties. So we can look at the total number of weights. Happens to be 6, but the trainable weights are only 3. So remember, we set our bias vectors to be non-trainable. So each of these layers have two variables, the W and P. W is trainable, but B is not. So in total, we have 6, 1, 2, 3 times 2. And then, but 3 of those are non-trainable. And then our output has shape 3 by 1 because we passed 3 inputs, which were 64-dimensional, but then the output is only 1-dimensional. Okay, so that's it about layers. Any questions up until here? All right, if not, you might be wondering, okay, this is already looking pretty much like a neural network. I can compose the layers together, and that is a neural network. So how is this different from a model? And the answer is, it is not really different from a model. It's only different. The only difference lies in what methods are available to the layers class versus the models class. So as we will see, model is very similar to a layer class, but it has some extra methods available to it, which help with training, evaluating, then also saving and loading the models, right? Okay, so for the next 2 sections, defining models and then training, I'm going to talk about 3 different ways of doing each. So I'll start with the simplest, the most high-level way of doing it. So that requires the least amount of coding. It's conceptually very easy, but then it has less flexibility. So for models, we can define it 3 ways. First is sequential, and we did this last time too. So sequential is very simple. You can just call tf.sequential, and then just pass a list of all the layers in the same order that you want your data to go through. So the first layer is an input layer, then a dense layer, then a ReLU, nonlinear activation, another dense, another ReLU, another dense. You can also just call model, you can instantiate a sequential model and then just call model.add and sequentially add the layers, right? So the first layer is the input layer, then dense, ReLU, and so on. So this is how we built our model last time. And let's just do this once again. So again, this is very similar to this MLP block that you built up here. But MLP block here happens to be a layer, but this happens to be a model. And you will see why this is useful, because then once it's a model, then we can train it very easily by calling the fit method on it. So let's just do that. First, let's just call the model on an example input. And so just to check everything works out, then we can print a summary of the model. This is another handy method that's only available for model class, but not layers, I think. So you can see what your model looks like. And so on. So if we were to train it, we could compile it and then train it. But before doing that, let's actually discuss another method of defining model. Once we have, I think, discussed all the methods, then we will go and actually look at how training works. So the next method is what's called functional API. So remember, with sequential, as the name suggests, the model has to be sort of a linear architecture, right? So if you have a new non-linear architecture, you can't really define it with a sequential method. By linear, what I mean is each layer is connected to one layer before it and one layer after it. But if you wanted something like two layers that are connected to a single layer, and then similarly one layer that diverges into two or more layers, that kind of architecture you cannot define with the sequential method here. But with the functional API, you can easily do that. So how would you define a model with functional API? Let's first define the above model, once again, with functional API. So here you actually write out the computation, describe the graph, and that just sort of defines the model itself naturally. So what do I mean by that? I start with an input, just give it a shape. So whatever shape my input is supposed to be. Then I pass that input through the layer that I want the input to go through. So a dense layer with 32 neurons. It gives me some output X. And I take that output and pass it to another layer. It wants to be a ReLU. That gives me another output X. Again, take it and pass it through another layer, and so on. Finally, I pass it through this final dense layer, and it gives me outputs. Then I define my model based on this graph that I described above. I just call tf.keras.model with capital M, and I just have to specify in this graph what are the inputs and what are the outputs. So the input is this, and the outputs are again called outputs. I can give it any name, and that's it. And then I can call model.summary, and it should be similar to the model we defined above. But okay, so nonlinear topology, how do we define with functional API? So for this, I'll just give sort of a silly example. It doesn't have to physically make sense. But let's say you have a model that's trying to predict the temperature and humidity on any given day based on some other weather data, right? Let's say what is the pressure, precipitation, how cloudy it is, and how windy it is. So given those inputs, maybe our model is trying to predict temperature and humidity. This doesn't probably make sense physically, but just to illustrate the idea of multiple inputs and outputs in a nonlinear topology in a model. So first, we have to define all of our inputs, right? So I'm just calling it pressure input, precipitation input, and so on. And these are all input layers. And I give them the appropriate shape. So each of these are just one numbers, I'm supposing. So all of these are one dimensional. Then I also give them their respective names. So it's easy to go back to them. So given that, then first what I do is I gather together the pressure and precipitation inputs and pass it through one branch of my model. So I just call concatenate layer on pressure and precipitation input. And then I pass it through a dense layer with 32 units, and then another dense layer with 16 units. Then similarly, I create another branch of the model where I collect together how cloudy it is and how windy it is. And then again, I pass it through a dense layer with 32 units and a dense layer with 16 units. So right now I have like two branches. One is processing pressure and precipitation. Another one is processing cloudiness and wind level. So given these two branches together, now I want to like combine them and then process them a little more and then predict temperature and humidity. So at this point, I want to merge these two branches together. And how do I do that? Well, you just call concatenate method again, based on this output X and this output Y. So we concatenate those two together. And then we pass them through another couple of dense layers. And now is the time to split, for example, the model. So now I want to go into one branch that predicts temperature, another branch that predicts humidity. So all I have to do is create a dense layer that takes Z and predicts temperature, another layer that takes this output C and predicts humidity. And now I can define my overall model. Once again, with functional APIs using tf.keras.model, I just have to define what are my inputs. So this time my input happened to be a list. So all of these that I defined up here, I'm just passing them in a list here. And then my outputs are temperature and humidity, which are these two here. And then I can give my model a name. So let's do that. And once again, you can call model.summary and it will print out. And this might be actually a little hard to interpret. So you see, like we start with input layers and then we go to concatenate. And it tells you what this layer is connected to. So this one concatenates pressure and precipitation. And then this, another concatenate _1 is connected to clouds and wind. Then we pass these two concatenates through a number of dense layers. So dense 9, this is connected to concatenate. And then dense 11 is connected to concatenate _1. And so you can see, like, you can go through this and make sense of it, but it could be a little hard to interpret. Luckily, you can also call this plot method or plot model method, and it will sort of visually give you the topology of the model, and it might be easier to interpret. So here we can easily see pressure and precipitation, we concatenate them together, pass through two dense layers, similar clouds and wind, concatenate, pass through two dense layers. Then we concatenate those two together, so these two branches. We pass it through a tail, and then we split it again to predict temperature and humidity. If this line of code doesn't work for you, it would complain that a certain library is not installed. Then all you have to do is to install that, and then it should work. Okay, so that's the second way of defining a model. Any questions up until there? Okay, so last method, which is I think the most fundamental or the most lower level way of defining models, is actually through subclassing. So now this should be very similar to the layers method, how we define layers. So again, I'm using a class to define a model, but instead of subclassing from layers, I'm just subclassing from tf.keras.model. Similarly to last time, I have to initialize it, just give it all of the layers in the model. And then I have to define a call method, which gives me the forward pass. So given an input, it should pass through dense 1 first, then ReLU, then dense 2, and so on. So exactly the same as how we composed layers together for a layer class, but now we're subclassing from model. So if we do that, it should work again, and we can call model.summary, and everything should work. So that's 3 ways of defining models. Now we can discuss 3 ways of training the model. And once again, going from the simplest and highest level method to the most fundamental level, which gives you a lot of freedom in defining how training proceeds. Any questions? Okay, if not, so let's go through training. And once again, I'm going to use the MNIST dataset as an example. We used this last time. In case you're not familiar, these are examples of handwritten digits. And we have split them into training images and test or validation images. Training images have 50,000 images, and test or validation set has 10,000. And these are 28 by 28 black and white images. So let's just quickly define our model once again. I'm just going to use this functional API method to define the model. So it takes the 28 by 28 black and white image and predicts what digit is in the image. So that's why we have 10 neurons here. So the highest level description is we can just call model.fit. So as long as this collection of layers is inside is a subclass of model, then you can call model.fit method. So that is very simple. So first, you just have to compile your model. You have to tell it what optimizer to use. what's the loss function to use, and any additional metrics that you want to keep track of. Once you compile it, then you can just call .fit method, give it what are the training inputs or images, what are the training outputs or labels. You define what's the batch size, so at a time how many images to train on, how many epochs to train on, and you can also give it the validation data. So at the end of each epoch, it will give you the loss and the accuracy on the validation side. So we can do that. And again, this should be a lot faster for you. If you're on a GPU, I'm on a CPU, so it's kind of slow. But you can see as the training progresses, it gives me loss and accuracy, accuracy is what I give in the metrics. And then at the end of each epoch, it should print out the loss and accuracy on the validation set as well. So as it's training, I can see if there are any other questions. Okay, how to install PyDot and GraphViz. So I'm not too sure about Hall. I think on your own computer, it should be straightforward. On Hall, we can probably take it offline after the tutorial. And I think there might actually be a Conda environment where this is installed. I was just not aware of it. Because obviously I ran this notebook in the past sometime and it worked, but today when I was working, it didn't work. So perhaps I worked in a different environment in the past where there was. So yeah, sorry about that. I don't have clear instructions about how to install it on Hall at the moment. Okay, so at the end of the epoch, as you can see, it also prints out validation loss and validation accuracy. So we can do that. And remember, we are collecting the outputs of this fit method in something called history, and history happens to be a dictionary. So if you look inside the history, it will have the loss and accuracy and validation loss and validation accuracy for all of the epochs that you trained. Okay. So this is for the first epoch, second epoch, and so on. And then for a model, you don't only have fit, but you also have convenient functions like evaluate. So if you give test images and test labels and evaluate them, then it will also print the loss and accuracy on those. Lastly, if you don't want the metrics and loss, but you just want the predictions, raw predictions, then you can also call .predict method. And then you don't need the labels, you just need the images. And this will give you the predictions, which will have shape 10,000 by 10. Once again, 10 because we have 10 neurons in the last layer. Yeah. So before proceeding to the next level of training, just a small aside. How do we train if we have multiple inputs and multiple outputs, right? So in the model that we described above, in this funny little weather model, how would we train that? So again, the only difference is in the compilation and fit method steps. So during compiling, again, you have to define what the optimizer is. But when you move to loss and metrics, you can give different losses for different outputs. So let's say if my temperature was a continuous variable, like I'm just trying to predict as a float the temperature, then I'll use the mean squared error for that. But let's say for humidity, it's a categorical, right? So let's say maybe I'm trying to predict low, medium, high. So I only have 3 categories. Then I can use categorical cross entropy for humidity. So depending on the nature of your output, you can use different loss functions for them. Same idea for metrics, right? So temperature happens to be a continuous variable. So for example, I can use mean absolute error. And then humidity, again, is categorical variable. So I can just use categorical accuracy on that. So you will just compile the model differently, and then it should work in the fit. I think one thing I didn't mention here, but is like in the fit method, you just have to make sure that your inputs and outputs are, again, are lists of like 4 inputs and 2 outputs. Okay. So then the next question is, can you modify what happens inside the fit method, right? Perhaps like for certain examples, I might want to give them more weight, and other examples I might want to give them less weight, or you can think of any number of things, right? You might want to change what happens inside the fit. You don't just want to go with the default behavior, then how would you achieve that? And that's very simple. So this is the next level of training. And you can do this by just defining another method inside your model class. So for example, here, I'll just define a custom model once again. And previously, you remember I initialized my model and then also had a forward method. But this time, I'm just defining a train step. So this definition will change what happens inside the fit method. So here, I'm not going to change anything. I'm just going to write the fit method once again. But this is where you can change things. So given the data, first I'll grab my inputs and outputs out of the data. Then I'll start a gradient tape. I'll gather the predictions by running the data through self, right? Now self, what does self refers to? It refers to the model that I have. And I have to make sure that I pass training equals true, so that if certain layers or variables have different behavior based on training versus inference mode, then they inherit the right methods. So I go do the forward pass, compute the loss, and then I come out of this gradient tape. Now I have to update my trainable variables. So I have to first collect them all. So I can call self, which refers again to my model, .trainable variables. This will give me a list. And then I can call tape.gradient of loss with respect to all of those variables. So now I can potentially have millions of variables here. So once I have the gradients, then I need to update those trainable variables, right? And how do I update them? This will depend on what optimizer I'm using. So once again, I'll call self.optimizer. So during compilation mode, I specify an optimizer. So it will have access to that optimizer. And then apply gradient. And so you just call apply gradient and you zip gradients and trainable variables together. So this is basically, instead of doing like going through all of the variables and doing assign sub with the gradients, you can just call this method and it will do it for potentially millions of variables. It will just update them all. Once you've updated them, then if we go back up here in the fit method, it gives you the loss and the accuracy. So if you want to keep track of those, then you have to instantiate loss tracker and accuracy tracker, which I did up here. So you can go to tf.keras.metrics and start some trackers for loss and accuracy. So once you have initialized those, then down here, you can update your state by passing to the loss tracker the loss, and to the accuracy tracker your predictions and the crowd truth values. But this is optional, right? So this part and this part is optional. If I've just listed it here in case you want to keep track of them. And then at the end of each epoch, if you are keeping track of loss and accuracy, then you can return those in a dictionary, just as the dictionary we had above up here. And then this, I'll let you read on your own. But again, this has to do with the trackers. If you're using the trackers, we want to reset them at the end of each epoch. So you have to call this method. But I really want to say, right now, we don't want to focus on this. So what we need to focus right now on is how is the fit method defined? The fit method is defined here. And so if you want to change anything, you just need to change the definition here of train step. And once you've done that, then you can just redefine your model. And now when you call fit method, it will use this definition instead of the default one. Okay. Okay, so that's the second method. And then let me just describe the last method, which is, if this sounds confusing to you, you can forget all about it, changing the fit method, because you can write the training loop from scratch and just go to the very low level of defining what happens during training. So that the third method I'm calling training loop from scratch. And how you do that is, once again, first you have to define your model. Then your data is, let's forget this for now, but let's say I have some kind of data generator that gives me 16 images and 16 labels at a time, right? Then you just have to initialize your optimizer, what optimizer you want to use, what loss function you want to use, any metrics you want to keep track of. So just initialize those. And then you just start a for loop, right? So I define how many epochs I want to train in, and then I go through that many epochs in a for loop. Then I just grab my training data set, my validation data set, and test data set. Then I just go through batches from the training data set. This is my training loop. So for step, and then inputs and outputs, and then enumerating my training data set. So I collect those. I start a gradient tape. I call my model on my batch of inputs, setting training equals true. That gives me the outputs, which I'm calling logits here. Based on the output, I compute the loss. So my loss function was defined up here. I use that, but I can also use any custom loss function here, because this is under a gradient tape. Then I compute the gradients of the loss value with respect to trainable weights of the model. And then I use my optimizer, which also defined up here, to apply the gradient and update the parameters. Then if I'm keeping track of metrics, again, I can update the state of those. And let's see, now here is an example of like changing things. Let's say after every 200 batches, I want to print out a few things. Let's say whatever the loss is, and then just also print out how many images the model has seen so far. So that's my training loop. And after the training loop, I can just gather the training accuracy, print that, and reset the training accuracy metric. And then at the end of each loop, training loop, I can also go through validation data, and I can collect predictions again, but going through batches of validation data set. But this time setting training equals to false, because we're doing inference, collecting any validation metrics, and then just printing those out. So if you run this, then you would see that after every 200 steps, it will print out the loss, and it will also say how many images the model has seen so far. And so with this, you know, this whole method here, you can like define your model, define what kind of optimizer you want to use, what loss function you want to use. If it's not already implemented in Keras or TensorFlow, you can define your own functions. And then you just have to write down this loop by hand. And if, for example, if the loss goes below a certain value and you want to stop, then you can add, for example, a break here, and the training will break. So that's an example. But anything different you want to do or extra, you can define inside this for loop. So that's, I would say, the lowest level of defining a training loop. And with that, I think I am done. This is all I had for today. So I'll take any questions. Oh, I should mention one thing. You will notice that this for loop will be significantly slower than if you were to use fit method. But you only need one line of code to make this as fast as the fit method. And I'll leave that as a homework for you guys. So somewhere here, you just need to add one line and it will make this as fast as the fit method. And I'm only not giving you that because I want to encourage everyone to go to keras.io and read the official tutorials that this tutorial was based on. So if I go to keras.io, go to guides, and so today's tutorial was sort of an overview of all of these. So if you want to go into more depth, please go through these tutorials. And that should be solid. So for example, customizing what happens in fit is like, I took some parts of it and put that in section here. And then writing a training loop from scratch. So please go through this and you will know what single line of code you need to add to make this as fast as fit. But yeah, that's it. So I'll take any questions. So I see one question, will you be able to upload this recording by the end of today? I'm not sure how soon, but I think all of these recordings will get uploaded. So Vlad, perhaps can you confirm when, is it like in a couple of days that these get uploaded?
Yeah, so hard to say. Our expectation is that they should be uploaded by the end of the week, but we still don't have the recordings uploaded from the previous two tutorials.
I see.
But yeah, they will be there. And there are already tutorials from last semester, which actually, have a significant overlap.
Oh, that's right. Yeah, so if you go to Center for AI Innovation website, I think, yeah, or the YouTube page for NCSA, you should be able to see the tutorials from last year. It's the same material, so you should be able to review. And yes, you can, another question is, can we use this notebook later? Absolutely. So the GitHub is public, so you can clone this at any time. And if you have an account on Hall, you can submit a job at any time for a Jupyter notebook. So you should be able to run whenever. All right, I don't see any more questions, so I will stop sharing.
Okay, well, Asad, thank you very much for delivering this tutorial. We really appreciate it. This is a valuable piece of knowledge that will be archived on our website and will be used by many, many people to come. So we really appreciate your effort here. And we are wishing you all the best, a new job and new life in a big city and all that. So all the best. Please come and visit us once in a while.
Thanks a lot. Yeah, absolutely. I had a great time at NCSA. It's an excellent place, and Vlad and Dave and everybody's help made it a very nice time. So thanks a lot for all the help in the past years, and yeah, I'll definitely look forward to coming back again sometime.
Okay, thank you. Thank you. All right, and we are done with this tutorial. So we will see you next week.